Hi, welcome to this video. My name is Philip. Today I will talk to you about some algorithms to find cost-effective patterns in some sequences of events. So we want to find patterns to understand the data, and there will be a concept of cost and utility, you will see. Okay, so let's start. So nowadays we have a lot of data in databases, so huge amount of data. And we want maybe to use some algorithms to find some useful patterns in the data that are interesting, unexpected, we don't know already, and can help us to understand or explain the data. To understand or also maybe to take some decision and so on. So to do this, there have been a lot of work on finding patterns in data, what we call pattern mining. There's a lot of papers about pattern mining. And in other work, people try to find all kinds of patterns in the data, like what we call the item sets. Item sets means some set of items or products that the people buy together. So for example, if you look on this slide, maybe some people buy cheese, noodles, and some orange juice and so on. This could be a set of items that people buy many times together in a database of customer transactions. So this is one type of pattern we can find. Other types is called the sequential patterns. Here we have also the time. So maybe a sequential patterns is we go to restaurant, then we go to the gym, then we go another place, university. And many people have this pattern, and then it can help to explain the data, for example. Other kinds of patterns is sequential rules, periodic patterns, subgraph in a graph. We want to find some subgraph repeating in a graph and so on. So why we want to find patterns in the data? The goal is to find some valuable hidden knowledge, something we don't know already, but is valuable to understand or take some decision. And also, contrarily to some other problem, like in machine learning and so on, we want to find the knowledge in the data that is interpretable by humans. That means we can really understand the data. It's not a black box model. Okay, so how to find useful patterns in the data? There can be millions of patterns in the data. So how to select the patterns that are interesting for us? We need to use some measure. We call some interestingness measures, such as the support. The support means how many times the patterns appear in the data. So if we want to look for the frequent patterns, the support means frequency, we can find all the patterns that appear at least a given number of times in the data. So maybe we find many people buy bread and milk together and so on. Some other measure I will talk to you about today is the utility. Utility is, for example, the money. So maybe we don't care about finding the most frequent patterns, but we want to find the patterns make the most money and so on. And there are many other measures proposed in the field of pattern mining. Okay, so a classic problem in in pattern mining is called frequent item set mining. So I will explain to you briefly. I will talk to you about some limitation. Then I will explain to you more, and then I will start to talk about the topic of today. So in frequent item set mining, this is a traditional problem. The input is a transaction database with many transactions, where, for example, the people buy some products we call items. So here we have transaction 1. It contains item A, B, C, D. Transaction 2 with A, C, D, D, E, and so on. So A could be, for example, apple, B for bread, C for cake, and so on. And the user needs to set a parameter we call the minimum support, here is 0.5. And the goal is to find all the patterns that appear in at least 50% of the transactions of the database. So for example, if we set this parameter to 50%, we find that C and D together, cake with item D, are about in 75% of the transactions. So why? Because C and D appear in T1, T2, and T4. So 3 transactions out of 4 that means 75%. So this is a very classic problem, find the frequent patterns in the data. But although it is useful, it does not consider the time. So time maybe is important. And also, it does not consider some other factor like the money. So even many people buy apple and cake or bread and milk. If you don't know about the money, maybe some sets of items are not so frequent but make a lot of money. So other factors like money and so on could be taken into account and maybe will be interesting to take into account. So to address this issue, it was proposed a new problem called high utility sequential pattern mining. The input is a quantitative sequence database where we have some quantities. So it is some sequence, for example, of events or items that have some values like quantities. So in terms of shopping database, for example, the first sequence could mean that we buy 3 apples, then later we buy 3 breads, then 1 cake, then 4 breads, and so on. Then maybe we have another customer buy 1 apple, 1 egg, 3 eggs, and so on. So here we have 4 sequences, and also we have some weights or unit profit. So we know that 1 apple costs $5, 1 bread $1, 1 cake $2, and so on. So the goal now is to find the patterns, some subsequence that appear in this database that make a lot of money or have a high utility. So to do this, we need to set a parameter called the minimum utility, such as 30 here in my example. And the goal is to find all the sequence of items or events that have at least $30 of utility. So, for example, just to show you how to calculate the utility of the money, if we take the sequence A followed by B, we buy apple and then we buy bread, for example, we say that it is a high utility pattern because the utility of AB in sequence 1 is as follows. So we have 3 apple. Apple is a $5, so 3 multiplied by 5. We have 3 bread. 1 bread is $1, okay? And then in sequence 3, we have 6 apple and 8 bread. 6 apple for $5 and 8 bread for $1 each. So the total amount of money of this pattern, apple followed by bread, is $56, and this is more or at least equal to the minimum utility. So we say that it is high utility pattern. So there have been a lot of papers about this, about designing some algorithms to find the high utility patterns in the data like this. So for shopping, but it could be also other things like some sequence of location instead and so on. Okay, so although high utility pattern mining is really popular now, there's a lot of papers about this, find the patterns that have a high utility, there are some limitations we want to highlight in this paper. First, all these papers focus on patterns that have a high utility, that means importance, but ignores the cost to obtain this benefit or this utility. So they may find some patterns that have a high utility, but that have very high cost. So I will tell you more about the cost later. The cost could be the effort, the money, the time we need to spend to use a pattern, for example. And it may miss some patterns that have a low cost but a high utility. So what I want to say here is that in high utility mining, we only focus on the benefit, the utility, but we don't consider the cost, how much effort or time we need to spend to get the utility. So we may find the patterns with high utility, but that also have a high cost, maybe not so important or interesting for us. Okay, so I will show you this with some example after. So in this paper, we propose a new problem called finding the cost-effective patterns. So we combine a concept of utility, like importance, but also with the concept of cost. So we want to find a good trade-off between cost and utility. We want to find the patterns that will give us the best utility at the lowest cost. So we call this the cost-efficient patterns. So here, what we mean by cost, there are many kind of cost we could consider. Cost could be the money or the time we need to spend to get the utility, or other kinds of resources we need to consume, or some effort, for example. Okay, so in this paper we study two problems that we think are important in real life. So we want to find the cost-effective patterns in sequences that have the cost value I will show you after, and where the utility is some binary values. So for example, I will talk to you about the medical data at hospital. So the binary value of the utility maybe is you are cured or you die after taking some medical treatments. So there will be the cost for the medical treatment, and the utility will be the result, like you get cured or you die. It is a binary value. And I will talk to you about the second problem, where the utility is some numeric values. Like, for example, in e-learning. So you pass some final exam, and the final exam, you have a grade. The grade is the utility value. It could be some numbers, like numeric values. So you pass the exam, you got 60%, or 90%, or 100%. So I will explain these two problems are a little bit different, how to find the good patterns that will give you the high utility with the low cost for these two cases. Okay, so let's look at the first patterns. We want to find the cost-effective pattern in sequences that have the cost and some binary utility values. So here I show you some example of data like this from the hospital. So here we have 4 sequences, some sequences of events. So we have some events like A followed by B, followed by E, followed by C, followed by D. And each event has a cost. So for example, the first sequence maybe is one person who go to hospital. Then it took some medical treatment A, and the cost was 4 hours. 4 maybe is the time or the money to take the treatment. Then another treatment B has a cost of 2, a treatment E cost of 4, C with cost of 4, D with cost of 5. And then the utility is a positive. Positive means like a good outcome, like you get cured. Or negative means maybe a bad outcome, like you die, and so on. So if we have a database like this, we want to find the cost-efficient patterns. The patterns that will have a low cost, but will make you cured, for example, in my example, will give you the positive utility. So how can we do this? So I will introduce the problem we propose. Later I will talk to you about the algorithms. So first, we need to use some measure to select the patterns. We will use the first measure is called the support of a pattern. This is not something really new. It has been used in many other papers before. So the support of a pattern is the number of sequences where the patterns appear. So if we want to check how many times the pattern AB appear, the support of AB, we will find that it is 2, because A followed by B appear in sequence 1 and also in sequence 4. So it appears in 2 sequences, so we say the support of AB is 2. So support is important because we want to find some patterns at least appear often enough, are not so rare. Maybe not so frequent, but maybe not so rare also. The second measure we will use to find a useful pattern is called the cost of a pattern. The cost of a pattern like AB is the sum of the cost values of the first occurrence of the pattern in each sequence where it appears. So A followed by B, it will be the cost of A followed by B in sequence 1, because we have A followed by B. So 4 plus 2 equals 6. And the cost of AB in sequence 4, so it is 2 plus 2 is 4. So 6 plus 4 equals 10. So the cost of AB in the whole database, for everyone who used this pattern, it will be 10. Okay, this is the total, the sum. But if we use the sum or the total, maybe not so interesting. It will be better actually if we use the average. So now I will show you another measure. It is called the average cost. So this will tell you on average, most people who do A followed by B, what is the average cost to do this pattern. Okay, so the average cost of AB is here is AB. We have AB in the first sequence with a cost of 6, and AB in the fourth sequence with a cost of 4, so 4 plus 6 equal 10, divided by how many sequences contain A followed by B, so this should be AB. 10 divided by 2 equal 5. So this is the average cost. Most people use AB. Usually they spend a cost of 5 to do this. 5 hours or $5 and so on. Now, the problem, we want to find the cost-effective pattern in the database like this, with the positive or negative utility. So we say that the pattern P is cost-effective if the support at least equal or greater or equal to some minimum support, and the average cost must not be greater than some maximum. So we don't want to find the patterns that have a cost that is too great. So these are the two constraints, and we want to find all the patterns like A followed by B, A followed by B followed by C that meet these two constraints. So we call this the cost-effective patterns. Now also, beside that, we use another measure we call the correlation of a pattern. So we want to see, for example, the pattern AB or AC, is it correlated with a good outcome, with a positive utility? So if you use AB or AC, do you have some good chance to get also a good outcome if you choose this pattern? So here, for example, we take the pattern AC. We find that the support is 3. It appears in 3 sequences. The average cost of AC is 5.3, and we want to calculate the correlation. So we will use some formula like this to calculate the correlation, where the correlation will be between -1 and 1. Below 0 means it has a negative correlation with a good outcome, and greater than 0 will be good. It means it has a positive correlation with a good outcome. So how to calculate this? Here we have the average cost of the pattern in the sequence where it is a positive utility, minus the average cost in the sequences where this pattern appears and it has a negative utility, divided by the standard deviation of the cost. And then here we have a square root, and we have the number of sequences that are positive and contain the pattern, multiplied by the number of sequences that are negative and contain the pattern, divided by the number of sequences where the pattern appears in positive or negative sequence. So with this, we can find some patterns like A followed by C as a positive correlation. So if we look at this, here we have A and C, it is positive. A and C, it is positive, and A and C is negative. But most of the time, A followed by C is a positive. Okay. So here we have more details in this slide about this. So why we subtract the average cost in positive sequence and negative sequence? We want to see if we do this because we want to see if there's a difference in terms of cost between the people that have the positive and negative utility. So for example, if we go to hospital, 2 persons do the same treatment, but one spend 10 hours, the other 5 hours, there's a big difference, then maybe the result, the outcome to cure or to die will be different. So that's why we subtract this. The standard deviation, we use this to avoid using the absolute values. And why we use the square root of this? We want to see if there's a difference between the distribution for this pattern between the positive or negative outcome. Does this pattern appear much more in positive or negative sequences, for example? Okay, so that's the main idea. So here I have a full example about this. I have a database, the one I showed you before. I set the parameter minimum support to 3, maximum cost to 10, and then I find many cost-effective patterns like this. So if you do A, you do B, C, D, and if you do A followed by C, B followed by C, and so on. So we can find that these patterns have different support values, they have different average cost, and they have different correlation. So here we can see that AC is a very good pattern because it has a very high correlation, for example. Okay, so there are some other patterns like B. It has a negative correlation. So this pattern may be not so good. Maybe it will not help to get a good outcome. Okay. So this was the first problem. Now I will talk to you about the problem number 2, where we want to find the cost-effective pattern in sequences that have some cost values but also some numeric utility. So here we look at another scenario. We don't have cure or die, but instead we have some utility that is some numeric values. So a sequence is an ordered list of events that each have a cost value. And then each sequence also has some utility that is some number. So we'll give you some example to explain this. Here we have, for example, some e-learning data. The first sequence, we have some student do some learning activity A and spend 4 hours, B and spend 2 hours, E 4 hours, C 4 hours, D 5 hours, and so on. And then the utility is the grade at the final exam, like 40%. So maybe this student has failed. Then another sequence, another student do learning activity B 3 hours and so on, but got 50% at the final exam and so on. So here, our goal is to find again the cost-effective patterns. We want to find the patterns that have a low cost. For example, means you don't need to study a lot to get the very high score at the final exam. So low cost and high utility. That means some patterns that are more effective. You will better spend your time to study to get the high utility. You will not waste the time, actually. Okay, so to do this, we use some measures that are a little bit different from the first problem I talked to you about before. So first, we compute the utility of a pattern. Since it is some numbers, we can calculate the utility, do the sum. So for a pattern like AB, the utility of the pattern is the sum of the utility of sequences where AB appears. So AB appears in sequence 1 and sequence 4. Sequence 1 has utility of 40 and sequence 4 70. So we say that the utility of AB in the database is 40 divided by 70, and we do the average, so divide by 2, because 2 sequences, the average is 55. So that means if you do AB on average, you can expect to get maybe a score of 55 at the final exam for e-learning. Okay, so now we want to study the relationship between the cost and the utility to see if you spend a lot of time, a lot of cost, how much utility you can expect. Is there a good trade-off between the cost and the utility to see is it an effective pattern? So for example, what we call the trade-off of a pattern P will be the average cost divided by the average utility. And it will give us some value between 0 and infinity. So lower will mean more efficient. So for example, let me show you some example. We have the pattern A followed by B. A followed by B appear in the first sequence and the fourth sequence. The average cost of A and B is 4 plus 2, 6. And here we have 4. So that means 10 divided by 2, so the average cost is 5, divided by the average utility for A and B. It was 55 we saw before. So that means the trade-off is 0.09. So that if we look at other patterns like C and D, the trade-off is a little bit higher, 0.13. So that means the pattern AB is more efficient than CD. We can assume. Okay. So of course these are just some measures, but it can give us some indication that AB should be more efficient. Because if we spend some time to do AB, some cost to do AB, then we expect to have more utility for the time we spend. The ratio is higher. Okay. So the second problem we study in this paper is for the numeric utility. We say we want to find all the patterns that are cost effective. We say a pattern is cost effective if the support is greater than some minimum support, the average cost is smaller than some maximum cost because we don't want to spend too much, and the utility, the average utility, is greater than some minimum also. So for example, we want to find all the patterns in e-learning that will give you at least an average score of 80%, for example. So here I show you a full example. I use the database you can see on top. I set the minimum support to 3, the maximum cost to 10, and the minimum utility to 50. So I will find different patterns. For example, I find some patterns that have the utility of 60. The pattern F has a very low trade-off, and it gives you a high utility. So 60. If I want to have utility lower, like 50 points for the final exam, I have different patterns like E, D, C, and D. And you will see that these patterns have different trade-off. So the pattern E has a better trade-off than D or C and D. So that means maybe it is a good patterns we could use to get the utility, if our goal is to get the utility of 50. Okay. So we can find many patterns like this. So now that I have presented the two problems, the first problem is to find the cost-effective pattern with Boolean utility. The second one with numeric utility. We need to define some algorithms to find all these patterns, to search for them. So we have two algorithms, CEPB and CEPN. So the first algorithm, CEPB, cost-effective pattern, B for binary, and cost-effective pattern for numeric, CEPN. So for the first problem, the second problem. So both algorithms will do a search. They will search for patterns in the data. They will use a depth-first search. That means they start from the empty set, nothing. Then they look for A. Then A followed by B. Then ABC, ABD, and so on. Then they backtrack. They do AC, ACD, ACE, and so on. Then they explore all the possible patterns by doing a depth-first search. So if you know a little bit about pattern mining, I can tell you also they adopt a pattern growth approach. That means they do some database projection and so on. So here I will skip the details about this. It is a little bit too technical maybe. So, but we don't want to look at all the possible patterns. So we need to use some search space reduction techniques. So we don't need to look all the patterns, but we want to find the solution. We want to find all the cost-effective patterns. So we'll use some special property, some new properties in this work. So how to reduce the search space using the cost? We define a lower bound on the average cost as follows. So here I give some formula, but I will explain with some example. So this lower bound on the average cost of a pattern we call AMSC, and we calculate like that. So I'll show you with the example. Let's say the minimum support is 2, so we do 1 divided by 2 multiplied by the cost, the min sub smallest cost value for this pattern. So here we have the pattern B followed by C. BC appear in 3 sequences, 1, 2, and 3. In the first sequence 4, in sequence 4, BC has a cost of 3. In sequence 2, BC has a cost of 5. And in sequence 1, BC has a cost of 6. So we take, because min sub equal 2, we take the two smallest cost value. Here it is 3 and 5, so we do 3 plus 5 divided by the support, it means 4. And this is a lower bound on the average cost. That means this value, the AMSC of BC, must be smaller than the real average cost of BC. It is a lower bound on the average cost. So why we use this lower bound? Because it has some special property. It will allow us to reduce the search space. So the property of this measure, the AMSC, are the following. Here we have one property, it is the underestimation. So the AMSC of a pattern must be smaller or equal than its real average cost. This is what I told you before. Another property is that important, the monotonicity. If you have a pattern PX like AB, that is a subset of another pattern like ABC, you know that the MSSC of the smallest pattern like ABC must be smaller or equal to that of the super pattern like ABCD. So ABC, ABCD. So if you have a super pattern, the AMSC must be smaller or equal to that of the sub-pattern. And then we have a pruning property for a pattern P. If the MSSC of the pattern P is greater than the maximum cost, then we don't need to look at this pattern. It's not cost efficient. And all the super pattern of this pattern are also not cost efficient. We can ignore them. So for example, if you have a pattern AB, the cost is too high, is greater than the maximum we want to find for the patterns, then we don't need to look at this pattern and all the extension of this pattern also. Okay, so we also have some pruning property to reduce the search space using the utility. Here I will explain quickly. We have some upper bound on the utility, 1 divided by the minimum support, and it is the sum of the utility of the pattern actually. So let me just show you this with some example. We have minimum support is 2, and we have a pattern ABC. ABC appears in sequence 1 and sequence 4. In sequence 1, the utility is 40, 4 is 70. So 1 divided by 2, the minimum support, and here we have multiplied by the sum of the utility, 40 and 70. So it gives you an upper bound on the utility, which is 55. So the utility, the real average utility of ABC must be smaller or equal than 55, because this is an upper bound on the real average utility of ABC. So again, we have some pruning property based on this. So I will go a little bit more quickly about this because similar to the other one. So if we have a pattern P like AB, if the upper bound of AB is smaller than the minimum utility, we know that AB cannot be the cost-efficient patterns, and all the super pattern of AB, like ABC, ABD, will not be also the cost-efficient pattern. So we don't need to look at all of them. So we can save a lot of time. So now, to tell you a little bit about the two algorithms, the first one is called CEPB, or core CEPB. Actually, we use two names in the paper. CEPB means without the correlation, and core CEPB means with the correlation. It's about the same thing. And CPN is for the numeric utility. So these two algorithms, one for the first problem, the other for the second problem, they both use a pattern growth approach. They do a depth first search, and then instead of looking at all the possible patterns, they will use the lower bound on the cost and the upper bound on the utility to reduce the search space. So here I will skip some other technical details about this that are not so important for today. Okay. So here I have a picture that shows some illustration of the search space. So we do the depth first search starting from the empty set. We look at A, AB, and then when we look at a pattern like AB, we check the pruning conditions. So if the support of the pattern is smaller than the minimum support, we don't need to look at the extension of AB, like ABC, ABD, and so on. If the lower bound on the cost is greater than the maximum, we don't need to look anything start with AB. If the upper bound is smaller than the minimum utility, we also don't need to look at all extension of AB. So using this, we can save a lot of time when we search for the cost-efficient pattern. So this is just the main idea. There are more details about this in the paper. Also, there's one technique in the paper we present. It's called the projected database buffer. So here I will not explain this because it is a little complicated, but this is just some optimization to improve the speed and reduce the memory of the algorithm. So the algorithm to search for patterns will extend some patterns. Let's say we have the pattern A, we extend the pattern to do AB or ABC and so on. And when we extend a pattern, we do some database projection. So we create a kind of copy of the database. So to reduce the amount of memory that we use, when we do a copy of the database, we use some special buffer. We call the projected database buffer. And this will reduce the memory and improve the speed of our algorithm. So here, I will not explain this in detail, but if you are interested, you can have a look, read the paper to see how it works. So it will just improve the speed of memory, decrease the memory. Okay, so we did some experiment now to evaluate the two algorithms. The first experiment is about the runtime, to see the speed. We want to see our algorithm with the optimization or the new lower bound on the cost will be faster or not. So what we did, we used 4 sequence databases that are used in the literature about sequential pattern mining. One is called Bible, Sign, BMS, and FIFA. We changed the max cost parameter to see how it influenced the time, the speed of the algorithm. And we compare ASC, this is the basic algorithm, our basic algorithm for the binary utility. Then with the improved lower bound, we call AMSC. And if we use also the projected database buffer, the special optimization, we see that it will be faster using this. For the other database, you can see similar result. So what this picture shows is that if we use the optimization that we have proposed, it can improve the performance of our algorithm. So we did the same for the other algorithm, CEPN. We compared different versions of our algorithm, and we see that there are some improvement when we use the AMSC lower bound and also the buffer technique. It will become faster. So you will see this is the fastest and so on. So this is just some performance experiment about the speed. We also did some performance experiment about the memory. So we compared the CEPB algorithm or CEPB with correlation with the algorithm for the numeric data, CEPN. And we used the lower bound or with the buffer and so on. And here we can see using the buffer, I did not really explain in this presentation, can reduce the memory sometime by 2 or 3 times because we use a special buffer to reuse the memory and so on. So here we skip more details about this. We have more experiment about the memory. Now, what I want to talk to you about that is the most interesting is the patterns we found in the real e-learning data. So to show that the cost-effective patterns are useful, we use some e-learning data. We try to find the patterns in e-learning data to find the cost-effective pattern about how to study to get a good grade or to pass the final exam. So we use some data that is public data from the DEEDS e-learning system. There was 115 students that did 6 learning sessions called E1 to E6. And the cost is the time to complete a session, and the utility means to pass or fail the final exam. So we have many sequences by students, and we have the cost, the time they spend on each learning session, and we have the result is a pass or fail, the binary utility. So this is the first problem we described before. So we apply our new algorithm to find the patterns, and we find several patterns you can see in this table. These are the patterns. For example, this may do the learning session 1, 2, then 5, and then 6. Here we have the correlation. So again, a positive correlation means a correlation with a positive outcome, like to pass the exam. We have the average cost, the amount of time. I think here it is some minutes. And we have the support, how many students have done this pattern. So on top, you see the positive correlation patterns that are positive, good patterns. And at the bottom, you have the negative correlation. All the correlation values are below 0. And in the middle, we have the correlation about close to 0. So we can find different types of patterns that have a positive or negative or neutral correlation. And this can be useful, we think, for the students to find some patterns maybe that are cost-effective, good ways of studying to get the good score, to learn more quickly maybe. Okay? We did a second case study with the e-learning data. Here we use the numeric utility. So here we look at one learning session inside, and in one learning session we have some learning activities inside. So one sequence, it is a student that has done some learning activities in a learning session. The cost is the time to complete the one activity, and the utility is the score at the final exam at the end of the session. So here, for example, if we use a minimum support of 0.1, max cost of 100, and we study the session 6, we find the average score is 14, and the most efficient patterns to obtain this score is some special activity, which has a trade-off of 0.63. For other learning sessions, we find other patterns and so on. Here I have a table that shows more patterns for the learning session 6, I think. So here we see we have many different patterns. They have different trade-off values. The small trade-off values is better, actually. And we have different average cost, different support. So we can find different patterns that will give different results and have a different trade-off between cost and utility. So in conclusion, in this talk, I have presented a new problem of finding the cost-efficient patterns in sequences with cost and utility information. We have presented two algorithms, CEPB, or we call also core CEPB with correlation, and CEPN for the numeric utility. We have presented some lower bound on the cost, some upper bound on the utility, and some optimization. And most importantly, for our new problem to show it is useful, we have used some real e-learning data where we had both the binary utility, the numeric utility, and the cost. And we find some patterns that look interesting that could tell some ways maybe of studying more efficiently to get a high score in e-learning system. Of course, this is just some preliminary experiment for the case study, but we could look at this in more details if this pattern really help the students and so on. So if you are interested in this work, the source code, the dataset are all available in the SPMF data mining library. If you search SPMF in Google, Bing, and other search engine, you can find the software, you can download the data, the source code, you can improve the algorithm if you want or apply it on your data. We published a few papers on this topic. The main paper was published in Knowledge-Based System. It presents the buffer, the special buffer optimization, and the algorithm I have described. That's all for today. Thank you very much for listening. If you want more details, you can read the paper, look at our software and so on. That's all. See you.